Portland State Aerospace Society, PSAS, asked us to improve the space-to-ground video capture and transmission system for their satellites. Our team focused on enhancing the software's reliability and integration to enable high school students to easily take selfies from space. Let's show you what we mean.
Today I'm going to show you a successful transmission between the satellite, which we have running on a BeagleBone Black, which has a USB hub connected to it, which has an antenna connected to it, and a camera. And it's going to be transmitting to the ground station, which is this Raspberry Pi over here, which also has an antenna connected to it. Have a terminal connection to each of these. So this is the Raspberry Pi, this is the BeagleBone Black, which is a satellite, and this is the Raspberry Pi, which is the ground station. And I'm going to show you the logs of the OLAF service. We're going to tail those, and then I'm going to show you how to transmit, which we could do through the browser. So here we've opened it up to the satellite's connection. This is achieved through the VCAN bus, which is set up through a package which starts it up, as well as the monitor interfaces on both devices are also started up by the packages and set into monitor mode. So here we check the state of OLAF through the read state button, and it says standby. That's a good state. So that means we can now start filming, which we do by clicking filming. And as we can see in the log here, it changed state from standby to filming. And it's currently recording frames and encoding video. As soon as it finishes that up, we will be good to go. I'm going to clean on the ground station any remaining videos just for the clarity of this presentation. There should be no more videos on the ground station, and on the satellite we see that it's finished recording the videos and they're available at this location. We can double check that and you can see video files there. So going back to the browser, on state, it's standby, which is a good state, and now we're ready for transmission. So we hit transmission. And you can see the state changed once again. And here we could expect to now see videos coming in on the ground station. And we can see that some did come in. So we should see, and we do see, a video on the ground station webpage. So that is an example of a successful transmission. As far as documentation, which outlines this in the Google Docs, which we wrote, you can find this under end-to-end transmission with OLAF application, and that will run you through all the same steps with additional detail on what is happening and how the services work. Alternatively, you can find very similar documentation on the satellite within the OreSat DX Wi-Fi software repo README. Specifically, you can go to end-to-end usage example, and you will see basically the same thing I just did here. As far as the rest of the components, the camera for the BeagleBone Black on the satellite, the documentation for that is in OreSat Live software. You could read this README, the camera README, and as far as the server, that is actually the server for the ground station, and you could read the README for the setup for that. That also has similar instructions to what I did today. And as far as what is actually achieving the transmission, which is the TX and RX commands, you can find that documentation in OreSat libDX Wi-Fi under transmit and receive for usage, and also you will see installation and packaging there as well. And that is all I have for you today. Thank you and enjoy your day. Bye-bye.
OreSat Live captures, encodes, and transmits video from space and receives and broadcasts it over Wi-Fi on the ground. College students build small satellites called CubeSats, install software including OreSat Live, and deploy to outer space. High school students build handheld ground stations, or HGSs, that receive and stream video of themselves from the satellite. OreSat Live was built primarily by a previous PSU computer science capstone team. And it basically worked, but the problem that the sponsor brought to us is that it was difficult to build, incompletely documented, and not integrated with the OreSat Linux app framework. The target audience of our project consists of two segments. College students, mostly undergrad, build, maintain, and deploy the on-satellite software. No software experience is assumed unless maintaining the code. High school students build in HGS and receive video of themselves from the satellite. No technical expertise is assumed. Onboarding, build, and use should be easy for both groups.
Hello, my name is Natnael Yohannes, and I'll be talking about our main achievements. Our project aims to enhance the efficiency and user experience of the build and installation process. This involves optimizing the steps required to set up the system, ensuring that they are straightforward. We focused on reducing complexity involved in the process, making it more accessible, especially for users who may have little technical expertise, as well as integrate OreSat Linux app or OLAF. We developed CMake build configuration to streamline the compilation and installation of the camera software, as well as package the camera software to ensure a more consistent and reliable build process. We created a Debian package for HGS web server. It includes startup scripts and systemd services in package to facilitate automatic starting in case of a reboot or a crash, as well as managing the web server. We also created a Debian package for the new OLAF app, as well as fixed numerous issues with version dependency, permissions, and just generally the flow of software along the way. We prepared a comprehensive step-by-step documentation aimed at users with minimal to no prior expertise with Linux. As well as we added a comprehensive documentation for user admins. This includes a complete list of the prerequisites necessary for a successful installation and operation of the software. We supplied example command line to illustrate how to execute various tasks such as installation, configuration, and operation of the software. We clarified the distinction between required and default parameters within the software configuration, as well as provided in-depth explanation on what each step in the process is doing. We outlined the components stored in the separate repos and how they interact with each other. OLAF is a Python can open application framework for all OreSat Linux boards, meaning OLAF is entirely written in Python, but the core components of the libdx Wi-Fi is written in C. Thus, we developed Python binding for libdx Wi-Fi to integrate with OLAF, as well as have more precise control over libdx Wi-Fi. OLAF app manages the state of machine, as we'll discuss more in detail in the architecture section. But the gist of it is that we send message from the ground to the C3 controller card, which then forwards it via CAN bus to OreSat Live card, and through that you could do all the goody stuff that the app could do.
We worked hard, but some future work remains to be done. For one thing, we should try to improve cross-browser reliability for the HGS web app. We found that it didn't work on Firefox for Linux or on some smartphones. We should also fix crashes where possible. The receiver crashes intermittently due to memory bugs, likely in the third-party OpenFEC library, which hasn't been maintained since 2016. Our current workaround is to restart the receiver automatically when it crashes. Also, transmission crashes the OLAF app unless we run it in a separate process, which we currently do as a workaround. Transmission itself succeeds in the case of a crash, but we'd like for there to be no crash. We should create a Python package for the OLAF app and upload it to PyPy. This is something PSAS wanted, and we didn't get that far. The OLAF app is currently in a Debian package. Similarly, we should package the libdx Wi-Fi Python bindings better. We should encode and transmit video directly from memory without writing to disk. Currently, we capture frames, write to disk, encode those frames to video, write to disk again, and then stop capturing and transmit the video. The satellite uses a solid-state drive, so a limited number of disk writes are available. It would also be nice to transmit videos in the background while we capture and encode new video, instead of stopping capture while we transmit. Finally, there are opportunities to clean up code, do more error checking, and implement best practices. This is especially true in existing code that we didn't change. It would also be nice to clean up the Python bindings. We currently bind the main function from the C code, which works, but isn't the best practice.
My name is Pranaw, and I'm here to describe the architecture of our project. The previous Capstone team created this beautiful diagram that you see in the middle of the screen to describe the OreSat Live system from start to finish. Since their Capstone, the hardware side of things hasn't really changed that much. The only notable change is the Raspberry Pi Zero W. Currently in our dev kits we're using the Raspberry Pi 3B+, but in theory any Raspberry Pi with sufficient ports should be capable of running the ground station software. On the software side of things, there have been a lot of changes. The diagram that you see on your screen shows how the 2021 Capstone team's work fits with our own. Feel free to pause the video in order to truly grasp the diagram. Notably, the camera portion of OreSat Live software has been fully integrated to OreSat DX Wi-Fi software. OreSat DX Wi-Fi software is the application that will run on the satellite to control all of OreSat Live's functions. The OreSat Live software server portion is still necessary to be run on the ground station, and OreSat libDX Wi-Fi is still required to build the Python bindings that OreSat DX Wi-Fi software uses for transmission. The diagram that you see on the right outlines the start-to-finish data flow from the satellite to the handheld ground station. I would advise that you pause here to take a look at the diagram for yourself. At the start of the data flow diagram, we can see the user of the OreSat DX Wi-Fi software app. This user could refer to both a person pressing buttons on the OreSat Live page or the C3 node sending a message over the CAN bus. The important part is that either calls a read or write of the status object defined in OreSat OLAF. Depending on the state that's being written, an action will occur. Something to note is that the OreSat Live service can initiate filming or transmission. Logically, filming should occur before transmission. The diagram below represents the state system used by the OreSat Live service to initiate an action. Again, I recommend that you pause the video in order to truly comprehend the diagram. Once a valid state write is called, OreSat DX Wi-Fi software will trigger an action based on it. Filming and transmission are currently the only states that trigger action. Currently, the actions are blocking. You should not be able to call any other state changes while the actions are occurring. Filming triggers a capture of frames based on the presets in camera_configs.yaml. Those frames are then encoded into video and placed in the video directory. Transmission will cause all the files in the video directory to be transmitted. Transmission has its own set of configs in transmission_configs.yaml.
Talk about our development process. We began with an agile process with 1-week sprints. Our sprints became less formal over time as individual tasks tended to balloon in complexity. However, we continued having weekly internal stand-ups, as well as weekly status meetings with our sponsor and technical advisor. These were a useful place to get feedback on ideas and to get help with technical hurdles involving the existing software framework. We also had a priority shift at the beginning of Q3. Our initial goals were build improvements, docs, and performance test functionality. We viewed the OLAF app as a nice-to-have. However, at the beginning of Q3, the main focus shifted to the OLAF app and to an end-to-end demonstration of the entire system. The performance testing goal was dropped. This was due in part to the loss of a team member, as we'll discuss later. Let's discuss responsibilities and contributions. Pranaw created the OLAF app, as well as architecture and data flow diagrams. This consisted of transforming and integrating existing video capture code and integrating transmission by calling the new libDX Wi-Fi Python bindings. In the process, he laid the groundwork for future implementation of video capture code in pure Python. It currently calls a C binary via the subprocess module, which is less than ideal. He also implemented a temperature sensor for telemetry data. This isn't part of OreSat Live strictly, but was requested by our sponsor and plugs into the OLAF app. Natnael created Python bindings for libDX Wi-Fi. This was critical for writing the OLAF app cleanly without more subprocess calls. Natnael also created a draft of a bit error rate test for transmission and receiving. This was one of our tasks during Q1 and Q2, although it was eventually backburnered due to other priorities. Alex wrote the majority of the documentation, created build and packaging scripts for all the software, fixed issues with the web service, and performed end-to-end testing. I performed code review and refactors as well as team lead duties. Along the way, we encountered a few unexpected events. One was Olaf v3. A major change to the framework was released while Pranaw was developing our Olaf app. Pranaw familiarized himself with the changes and updated his in-progress work accordingly. Another was changing Python bindings requirements. Initially, any binding library was deemed acceptable as long as it got the job done. Natnael started by using the ctypes library. Then the directive was to use either Swig or PyBind 11 because they're simpler to use and maintain, so Natnael started using Swig. Finally, we were directed to use PyBind 11 in order to align with some existing Olaf apps, so Natnael restarted using PyBind 11. We also dealt with the loss of a team member in Q2. A former teammate was inactive throughout the first 2 quarters and eventually left the project at the end of Q2. We met with our sponsor and reevaluated priorities and feasibility, and we settled on an achievable plan of work that met core needs. We realigned team members to this new set of deliverables. So, what feedback did we get from our sponsor? We gave a full, from-scratch, end-to-end system demonstration. Our sponsor gave it a 6 or 7 out of 10. All core functionality worked to everyone's satisfaction. However, the demo, as well as the documentation at the time, was scattered and hard to follow. Our sponsor noted that they often struggled to follow exactly what we were doing and why. Since then, we've improved the documentation significantly, and we've resolved the issues that caused hiccups in the demo. We've reached out to our sponsor for any additional feedback and are awaiting a response. Our software is planned for deployment on the next satellite, OreSat 0.5, in Q1 of 2024. And what did we learn? First, a rapid feedback cycle is critical. It's really helpful to create draft pull requests early for in-progress work. Work does not have to be complete in order to benefit from review. We can evaluate merits of an approach early and avoid wasting effort on a suboptimal one. Also, the entire team can help a person get unstuck when we can all see the code. Similarly, it's a good idea to run plans by stakeholders early before investing effort in them. For example, perhaps we could have saved time on Python bindings by getting more explicit approval on our exact choice of library. Second, be eager to ask for help and clarification when needed. If a subject matter expert is available, ask lots of questions. We can take advantage of their knowledge rather than spinning our wheels trying to figure things out from scratch. Finally, don't underestimate the value of domain knowledge. We were advised early that teams working with PSAS have historically already had experience with PSAS. Hardware setup and getting familiar with the ecosystem and context were hurdles early on. And to conclude, we'd like to thank Andrew Greenberg, Ryan Medic, Russell Sr., and everyone in PSAS and the OreSat project, and of course, Bruce Urban.